You will notice when I showed you the first example of a radical reaction that I used a cyclohexane and bromine, much like Professor Pelkey's notes have. And I should also point out that you could use cyclohexane and chlorine to generate the chlorocyclohexene product. Again, the main idea is you can simply use a bromine or a chlorine type species in order to functionalize an alkane. And the reason why Professor Pelkey and I both started with cyclohexane is because there's really only one product possible. There's only one type of hydrogen present here. There are 12 different hydrogens, but every single one of them is exactly the same, and so there's going to be no selectivity, and so you get bromine on one of the various hydrogens. And likewise, if you throw in chlorine, you're going to get chlorine on one of the hydrogens, and it's as simple as that. However, as soon as there's possibility of deciding between species, then what you're going to notice is that the difference between bromine and chlorine becomes quite important. So if we have something like this, and we count out the total number of hydrogens of each type, what you'll notice is that we have two different methyl groups, so 6 hydrogens that are entirely primary but similar to each other. Then we have a third type of methyl group, which is to say you now have 9 hydrogens of the primary type, and then you have 2 hydrogens that are secondary, and then you have a hydrogen that is tertiary. So how many different potential products are there? Well, if you run the reaction with bromine, you will find that it is incredibly selective, and it is selected for the tertiary position over all the others, and so this becomes synthetically useful. If I run this reaction with bromine, then the product that I make will be entirely at the tertiary position, or almost entirely anyway. However, when you run the reaction with chlorine, you make an absolute plethora of products. You can attack any of these methyl groups in order to give you a primary chloride. You'll get both stereochemical isomers, because as soon as you install a chloride, the methyls are no longer equivalent. This molecule here is a chiral, but as soon as you install a chloride, then it becomes enantiomeric. These are enantiomeric chlorides. You can also install the chlorides at the secondary position. You can install the chlorides at the primary position that does not lead to a stereocenter, or of course the chloride can end up at the tertiary position, much like the bromide. Now, I shouldn't lie and say that this is the only product that you will form, but if you look at the table of the relative rates of the reaction here, then you can start to figure out exactly what the problem is. Chloride is relatively indiscriminate. It will react almost as fast with the secondary substrates and the tertiary substrates. Those are nearly identical in terms of reaction rate. 4 times faster than the primary, 5 times faster than the primary, which is to say the difference between reacting with a secondary and a tertiary as far as the chloride is concerned is relatively low. Meanwhile, bromide is much more selective. If you have a relative rate of reaction with the primary of 1, then reacting with the secondary is 80 times faster, and reacting with the tertiary is 1600 times faster. There is a dramatic preference for the tertiary position over the secondary position, and a dramatic preference of the secondary position over the primary for the bromide, but there is really not much difference as far as the chloride is concerned. Essentially, that should tell you something about the energies involved. The chloride doesn't particularly care which hydrogen it abstracts, whereas the bromide is quite sensitive to the strength of the CH bond that it's abstracting. The message is bromides are going to be selected for the tertiary. You can actually do a calculation here and figure out what the relative amounts of everything that you're going to get are. Because there are 9 different hydrogens that are primary in nature, you also have a single tertiary and a pair of secondary. So we could figure out what the actual distribution of products is simply on the basis of statistics. After doing the Professor Pelkey riff, it's only right that I shift now to the Professor Miller handout and to look at his extended riff on the subject. And so the idea here is that he walks through the table for this particular compound. If we count up the total number of primary hydrogens, there are 9. So there are 9 hydrogens of the primary type. The relative rate of reaction with the chloride is 1, which means that you will make 9 of the primary products, relatively speaking. There are only 2 of the secondary type, but those react faster than the primary, so you actually end up making 8 products with those secondary substitutions. With the tertiary position, there's only a single hydrogen, and though you make that faster, you end up making fewer of them because of the statistics. So anyhow, there are 22 potential products where you do the substitution on the 9 primaries. You go 4 times as fast on the 2 secondaries, and you go 5 times as fast on the 1 tertiary. So there are 22 total. And so what do you end up making? Well, 9 out of 22 is about 40% of the primary. And in fact, there are a couple of different primary products, 3 different primary products. So you end up probably making about 13% each of those. So it's a relatively unselective reaction, even when you're just looking at the primaries. Likewise, you make 36% of the 2 secondary products, and you're going to make a racemic mix, and you make 22% of the tertiary product, which is to say you you make all of it, and though you can fish out maybe 22% of this, there's a whole bunch of other stuff present. By complete contrast, when you run the same exact reaction and analysis with the bromine, again, there are 9 different primary hydrogens, but the relative rate for a primary is only 1, but there are 2 secondary hydrogens, and the relative rate of bromination of the secondaries is 80 to 1, so you make 160 of these products relative to the 9 primaries. But then, of course, the tertiary position goes 1600 times as fast, so even though there's only a single tertiary hydrogen, you make so much faster that you get 1600 of those for 160 of these for 9 of those. In other words, of the 1769 potential products that you make, 1600 of them are at the tertiary position, which means you are going to fish out 90+% of the tertiary material. That is synthetically useful in a way that none of this is. Likewise, the second most common thing that you make is going to be the secondary position. You essentially make none of the primary position. Again, this is a very selective reaction with the bromine. It is almost completely non-selective with the chlorine. The Miller handout also points out that you simply don't run these reactions with fluoride, and that's because this is really non-selective. Fluorine is even more non-selective, and fluorine is dramatically faster. If you mix together fluorine and some alkane, you start a fire or you start an explosion, you cannot control the reaction no matter how hard you try. Whereas you can control the reaction with the chloride, it's just not synthetically useful, and the bromide is very synthetically useful. You cannot do this with iodides because it just simply doesn't react.